So yesterday we introduced the concept of volumes of revolution and used it to derive some formulas that we've already known. So a lot of people would say, well, so what, right? These are things that we already know. We can look those up. Why would we want to do this? Others might be saying, can I use it to solve this problem over here? And the answer for that is no. So it's good to go through the strengths and limitations of this process. So we will start with the strengths. So what good is this process? Well, the process that we have, remember, is to take whatever shape we have. Say we're looking at a Cheney vase, like that old episode of Alfred Hitchcock Presents. That one's public domain. I recommend checking it out. We can use it to figure out the volume of a vase. We can slice that vase into these various circles, add them up. All we need to do is figure out the function that we can use to express the side. Once we have the shape of this side, then we could say our volume is the integral from A to B. Here our A is 0 and our B is the length of the vase, of pi times that function squared, since that would be the radius of each of these circular segments, dx. So that is a huge strength of this technique. We can use it to find the volumes of arbitrary cylindrically symmetrical shapes. And in that, we've come up with our limitation. So the main limitations of this is that they have to be cylindrically symmetrical, or at the very least have to have an area that is easy to express. So if we don't have cylindrical symmetry, say we're trying to find the volume of a pyramid. That's a terribly drawn pyramid. Let's do it like this. So we have our pyramid and we're trying to find the volume of that. Well, we don't have a cylindrical symmetry, so we can't use that pi f squared dx version. We would have to go back to the integral of the area dx. So that version is a little more versatile. And if we could find a way to express the area of these squares in terms of the height as we move from the bottom to the top, well, then we're still in good shape. But that is the key. We have to be able to express the area of the cross-sectional shape. If we have something like a Klein bottle, and we want to find the volume of that, well, we're going to be in serious trouble, because this has gaps and weird things. It is a mathematical construct that really has no inside and outside. It is the volume equivalent of the Mobius strip that you may have heard about before, that two-dimensional shape that you twist around so it becomes a 2D shape with only one side. If you draw a line on one side, it'll come, get twisted around, be on the back. So there are limits to it, but that really the only limitation is that we have to be able to find a way to express the area of the cross-sectional shape. As long as we could find the area, or in the case of a cylindrically symmetrical shape, so one that looks the same in its cross-sections are circles, then we can use our pi f squared form as well. So these are the two keys. So for example, let's say we want to find the volume of a shape whose area is the square root of x. So you've got some kind of pointed bowl, and you've determined that the area, or that one side, can be represented by the root of x. We want to find the volume of that as it goes from 0 to h. Well, that we can do That is the volume from 0 to h of pi root x squared dx, or 0 to h of pi x dx, 1/2 pi x squared from 0 to h, or really the volume is going to be pi h squared over 2. Now you may be thinking, wait a minute, this is supposed to be a volume, but we only have h squared, it's part of the area. Well, that's the mathematical side effect of just saying, yep, the radius is root x. So we'd have an extra unit there that's not expressed, and that's how we're going to get up to our x cubed. So we have to be careful when we're doing purely mathematical constructs and doing our unit analysis, because sometimes they don't quite work out. So we're going to have to set unit analysis aside as we continue on to more examples with volumes of revolution.